Good morning, students. In the last session, we have discussed about some of the basic terms related to stereochemistry. In today's class, I will be discussing the next types of the isomerism. In the last class, that is, we have discussed about the first type, the main first type, that is structural isomerism. Let me revise the types of isomerism, that is types of structural isomerism in brief. In the structural isomerism, you have studied about different types, that is chain isomerism, position isomerism, then functional isomerism, metamerism, tautomerism. Chain isomers are nothing but that is compounds which are having same molecular formula but differ in the arrangement of carbon chain. That is, they differ in the arrangement of carbon chain. So such type of isomers we call as the chain isomers, and the phenomenon is referred to as a chain isomerism. The second type we studied is position isomerism. Position isomerism means here also the compounds will be having same molecular formula, but there will be a difference in the position of the substituent atom or group within the carbon chain. So such type of compounds are called as a position isomers. And the third type we studied is the functional isomers or functional isomerism. Here the compounds will be having same molecular formula, but they differ in the functional group. That is, they will be having different functional groups. Such type of compounds are called as functional isomers. Metamerism. The fourth type is a metamerism. Compounds which will be having same molecular formula, but they will be belonging to the same class of compound, but there will be a difference in the distribution of the carbon atom on both side of the functional group. On both side of the functional group, there will be a difference in the arrangement of the carbon atom or distribution of the carbon atom on both side of the functional group. Such type of compounds we called as a metamers, and the phenomenon is called as a metamerism. Whereas in the tautomerism, that is, the both the compounds will be in simultaneous equilibrium with each other, and they will be showing keto and enol forms of each other. So such type of compounds we called as a tautomers, and the phenomenon is called as a tautomerism. And the second type in the isomerism, first type was a structural isomerism, which is also called as a constitutional isomerism. The second type was that is stereoisomerism. In the stereoisomerism, we have studied the first type, that is geometrical isomerism. Geometrical isomerism is nothing but here also the compound will be having same molecular formula, but there will be a difference in the arrangement, that is spatial arrangement of the groups that we called around the double bond in alkenes, whereas about the single bond in cyclic compounds. Such type of compounds we called as a geometrical isomers, and the phenomenon is called as a geometrical isomerism. So next we'll see the second type of stereoisomerism, that is optical isomerism. Here optical isomerism means compounds which are having same molecular formula, but they can be distinguished by their action of a plane polarized light equally but in opposite direction. Such isomers are known as optical isomers, and the phenomenon is known as optical isomerism. Optical isomers means these are the compounds which have same molecular formula, but there will be a difference in the rotation of the plane polarized light. That is, their action on the plane polarized light is equal but in opposite direction. They will be rotating the plane polarized light in equal amount, or we can say same extent, but they will be rotating in the opposite directions. Such compounds or such isomers we call as optical isomers, and the phenomenon is referred as the optical isomerism. Now we came to know that the compounds will be rotating plane polarized light. So we need to know what is this plane polarized light. We know that ordinary light vibrates in all the planes perpendicular to the direction of propagation. The same light when passed through the Nicol prism, the vibrations takes place only in one plane. Such a light is called as a plane polarized light. We know that generally the ordinary light, see the diagram here, the ordinary light will be vibrating in all the directions, or we can say in all the planes. If I consider the, that is direction of propagation, this light, ordinary light, will be propagating in all the direction, that is in all the planes which is perpendicular to the direction of propagation. When once this ordinary light is passed through the polarizer, or we can say Nicol prism, it vibrates only in one direction. See this side, after the when it passes through the polarizer or Nicol prism, it vibrates only in one direction, or we can say in only one plane. Such type of light we call as a plane polarized light. The property of substance to rotate the plane polarized light is called as optical activity, and the substance exhibiting this property is called as optically active compound. We know that the plane polarized light, it is vibrating in only one plane. So the property of the substance to rotate the plane polarized light, that we call as that property of particular substance is termed as a optical activity. Optical activity is nothing but it is property of substance to rotate the plane polarized light. And the substance which is rotating the plane polarized light, or we can say which is exhibiting this optical activity property, such type of compound or substance is called as a optically active compound. The isomer which rotates the plane polarized light towards right clockwise direction is known as dextrorotatory and is denoted as positive symbol. The isomer which rotates the plane polarized light towards left anticlockwise direction known as levorotatory and is denoted by a negative sign. That is, we came to know that the isomer will be rotating the plane polarized light in either of the direction. It can rotate either in the right direction or in the left direction. That is, we can say in the clockwise direction or in the anti-clockwise direction. If the isomer is rotating the plane polarized light towards the right, see here, see the diagram. If it is rotating towards the right, then it is rotating the light in the clockwise direction. Such type of compound is called as dextrorotatory compound and it is denoted by a positive sign. If the isomer is rotating the plane polarized light towards the left or in the anti-clockwise direction, or we can say counterclockwise direction, then those compounds are called as a levorotatory compounds and they are denoted by a negative sign. See the diagram over here, we can say dextro and levorotation. If the ordinary light we are passing through the polarizing filter or polarizer, it vibrates only in one direction. See the plane polarized light vibrating in only one plane. When this light is passed through a sample solution, it will be rotating the light either towards the right side or towards the left side. It will be rotating either towards the left side or either towards the right side. If it is rotating towards the right side, it is called as a dextrorotatory compound and it is that is it will be denoted by a positive sign. If it is rotating towards the left side or counterclockwise direction, then that compound is called as a levorotatory compound and it is denoted by a negative sign. If it is rotating to a 20-degree angle, then it is denoted as a minus 20 degree. That is observed rotation. Alpha will be observed rotation is equal to minus 20 degree. Minus 20 degree indicates the anti-clockwise direction. Minus is, we are denoting minus, that is to indicate the levorotatory compound in the clockwise direction. Sorry, in the counterclockwise direction. The optical activity is measured with the help of the polarimeter and is expressed in terms of specific rotation. So this optical activity of the compound is measured with the help of an instrument that we call as a polarimeter. The instrument to measure the optical activity of a compound is called as a polarimeter. It will be containing a polarimeter tube and spectrophotometer. So that polarimeter instrument is used to measure the optical activity, and this optical activity is measured in terms of a specific rotation. So how we can define this specific rotation of a compound means the optical rotation produced by a compound when plane polarized light is passed through 1 decimeter length of the solution having a concentration of 1 gram per milliliter. That is, specific rotation of the compound is nothing but it is an optical rotation of the compound when we are passing the plane polarized light through 1 decimeter length of the solution. See here in the diagram, that is, this is called as a polarimeter tube. The length of this tube, or we are taking solution in this tube, so generally we refer it as a length of the solution. That is, here the specific rotation of the compound is the optical rotation when the light is passed through 1 decimeter length of the solution. It should be 1 decimeter length. And the concentration of the solution should be 1 gram per milliliter. And it is expressed as, that is specific rotation is expressed as alpha from T to lambda is equal to alpha by L into C, where alpha is observed rotation in degree, L is length of the polarimeter tube in decimeter length, C is the concentration in terms of gram per milliliter solution. That is, C is the concentration, L is the length of the polarimeter tube, alpha is the observed rotation in degrees. If the length of the polarimeter tube, that is L is equal to 1, C is equal to 1, then specific rotation would be alpha is equal to, that is alpha from T to lambda is equal to alpha. That is when the length of the solution and concentration of the solution will be equal to 1, or when they will be unit, then alpha will be equal to alpha, that is specific rotation of the compound will be equal to the observed rotation. This condition you have to remember, that is when the specific rotation of the compound will be equal to observed rotation only in the condition that when the length of the polarimeter tube and the concentration of the solution should be unity. Then the observed rotation will be equal to the specific rotation of the compound. Next we have the concept of chirality, that is the term chiral is derived from the Greek word that is chir, which means hand. The concept of chirality was introduced by Kelvin for those objects which have handedness, that is object and mirror image relationship of left and right hand. Chirality is nothing but it is a property of the objects, or we can say compounds, and this word chiral is derived from a Greek word that is chir, which means hand. And this concept was first introduced by a scientist called as Kelvin. He has introduced this concept using the example of a mirror hand relationship of the left and right hand. See the diagram here. If I hold the left hand in front of the mirror, we can see the mirror image of that is hand. The thumb will be on the same side, the other fingers will be on the same side, means if the thumb is on the left side, then in the mirror it will be on the left side. This we call as object and mirror image relationship. Next we have that is chiral carbon atom. The carbon atom which is bonded to 4 different groups or atoms is said to be chiral. Means if there is a carbon atom in the molecule, if it is bonded to 4 different groups or atoms, that type of carbon atom is called as a chiral carbon atom. And the center is called as a chiral center. See one example I have given here. This is a carbon atom. It is bonded to 4 different groups. It is bonded to bromine, chlorine, fluorine and hydrogen. The carbon which is bonded to 4 different groups is called as a chiral carbon, and this center is called as a chiral center. Object or molecules which are not superimposable on their mirror image are chiral and are said to possess chirality. Means if the objects or molecules, if they are not superimposable means if I keep the left hand on right side, first keep your left hand on right hand, see your thumb will not be on the thumb of another hand, means the left hand thumb will not be on the right hand thumb, the forefinger of the left hand will not be on the forefinger of the right hand. This we call as a non-superimposable, means they are not superimposable on each other. Superimposable means the thumb should be on the thumb means left hand thumb should be on the left hand thumb. But if I keep both the hands on one another, the thumb will not be on the thumb and the other fingers will not be on each other. So that type of compounds or objects we call as a non-superimposable or not superimposable. That type of compounds we call as means they should be possessing the chirality. If they are not superimposable on mirror images, are chiral and they are said to possess, or they will be having the chirality property. The chirality is the essential criterion for exhibiting the optical activity as well as for enantiomerism. If a compound or if there is a isomer, if it want to exhibit or if it exhibits the optical activity and enantiomerism, means it should contain at least one chiral carbon atom. That is, it should show the chirality property. Means if there is a compound, it want to exhibit enantiomerism or optical activity, then it should contain at least one chiral carbon atom. That is nothing but it should possess the chirality property. If a molecule or object is superimposable on its mirror image, it is achiral. Non-chiral, achiral molecules are optically inactive and cannot exhibit enantiomerism. If they are superimposable mirror images, if the object or molecule is a superimposable mirror image, then it is called as achiral, or we can say non-chiral. And these achiral molecules will be optically inactive, means they will not be showing any optical activity and they will not be exhibiting the enantiomerism. They neither exhibit enantiomerism nor they show the optical activity. Next we have enantiomers. That is, in the optical isomers, again we observe two types. One is the enantiomers, another one is the diastereomers. We can say enantiomerism and diastereomerism. In the stereoisomerism, we observed two types. One is geometrical, another one is the optical. In the optical isomers, again we observe two types of isomers. One is enantiomers, another one is diastereomers. First, we'll see what are enantiomers. Enantiomers are the molecules that are non-superimposable mirror images of each other are called as enantiomers. See here, these are the non-superimposable mirror images. Means they will be mirror images of each other, but they will be non-superimposable. See the image over here. See, these are the two hands, that is left hand and right hand. If we are drawing a mirror plane over here, both will be mirror images of each other. Means this side towards viewer side, my side, both there are thumbs. Both the side we have thumbs. So mirror image, they will be mirror images of each other. Means exactly they will be on the same side. Like the forefinger will be on the left side, thumb will be on the left side, means observer side, my side, whereas the middle finger will be similar to the middle finger on both the sides, left and right side. So there will be a mirror image of each other. But if I keep both the hands on each other, see, if I am keeping the that is right hand on left hand side, the thumb will be on the opposite directions, the four fingers will be on, other fingers will be on the opposite directions, means they will not be superimposing on each other. So such type of compounds or isomers we call as enantiomers. Means they should be mirror image of each other. Both the objects or molecules should be mirror image of each other, but they will be non-superimposable. Such type of compounds we call as enantiomers. See the example over here. We know that there should be a chiral carbon atom in order to be a enantiomer. If the compound should be enantiomer, then it should contain chiral carbon atom. See the compound over here. The first compound is having a chiral carbon atom. This is a chiral carbon atom. You have to remember here, if we are representing a chiral carbon atom, you should represent it with the asterisk. Asterisk is nothing but generally we refer it as a star on the carbon atom. Here this is a chiral carbon atom. Why? Because it is bonded to four different groups. It is bonded to COH, H, OH and CH3. So it is a chiral carbon atom. So it can exhibit an enantiomerism. If I write the mirror plane, then mirror image, these both the compounds are mirror images of each other. Means on the left hand side we have OH group, hydrogen on the same hydrogen side, COH group on the same side, then this side methyl groups. So both are having mirror images. But if I keep this second molecule on the first molecule, see here on the right side on hydrogen atom I will be getting methyl group. On that is on the methyl group I will be getting hydrogen group. Means they are not superimposable on each other. So this is an example for the enantiomer. See here, there are some of the features or properties of enantiomers. Enantiomers are stable compounds that differ from one another in three-dimensional spatial arrangement. That is, enantiomers are stable compounds, but there will be a difference in the arrangement in the three-dimensional arrangement. And enantiomers have an identical property in all the aspects except in their interaction with the plane polarized light. That is, they will be showing similar properties. If there are two enantiomers, they will be showing similar properties, means they will be having similar melting point, boiling point, or we can say solubilities. But there will be a difference in the action of the plane polarized light. Means they will be differing in the interaction with the plane polarized light. Both rotate the plane polarized light to exactly same extent, that is to same angle, but one rotate the plane polarized light towards the right while the other rotate towards the left. And that is, if there are two enantiomers, both will be rotating in the that is to the same extent, means same angle. If the first enantiomer is rotating to 10 degrees, the second will be rotating in the 10 degrees only, but they will be rotating in opposite directions. If one is rotating towards the left, another will be rotating towards the left. Means, for example, if there is a two compound, the first compound, if it rotates to the 10 degrees, the second will be rotating to the 10 degrees, but the first rotates either towards the left or towards the right, the second will also be rotating towards the left or right. For example, if the first one is rotating towards the right, I will be writing as a plus 10 degrees. Why? Because it is rotating towards the right, that is towards the clockwise direction. Clockwise direction means it is dextrorotatory, so it should be represented with a positive sign. So I will be writing as plus 10 degrees. Whereas the second compound, if it is rotating towards the that is towards the left, the first one is rotating towards the right, so we say that second one will be rotating in the opposite direction, so it will be minus 10 degrees. Why? Because it is rotating in the counterclockwise direction, so it is a levorotatory compound. It should be represented with a negative sign, so it will be minus 10 degrees. Next, we'll see the second type, that is diastereomers. Optical isomers which are neither superimposable nor mirror images are called diastereomers. Means these are the optical isomers which are not superimposable and not mirror images of each other. If I am taking two compounds, they will not be mirror images of each other, as well as they will not be superimposable on each other. See the example here. Here we have same molecular formula. You are observing two compounds, both will be having same molecular formula, but they are not mirror images of each other. See here, if I write the mirror plane in between here, on the right side of the first compound we have three hydroxyl groups, whereas see here on the right side of the, and that is, if I write here mirror plane, on this side, on the mirror side, there will be two hydroxyl group, one hydrogen atom. Means these are not mirror images of each other. You are not getting a mirror image of each other, so they are not mirror images of each other. That is the first condition. Second, they are not superimposable. Not superimposable means if I keep this second compound on the first compound, on the right side there are three hydroxyl groups. If I am taking the second compound and keeping it on the first compound, on the right side you will be getting two hydrogen atoms and one hydroxyl group. Means on the hydroxyl group we will be getting hydrogen, on the hydroxyl, second hydrogen, on the third hydroxyl you will be getting hydroxyl group. Means on this you will be getting different groups. Means they are not superimposable on each other. These compounds we are calling as a diastereomers. Means they will not be superimposable, as well as they are not mirror images. So such type of compounds will be referring as a diastereomers. And these diastereomers have different property, and two diastereomers will have different melting point, different solubility. They will have different reaction towards most reagents. See here, whereas the enantiomers, we know that they will be having similar properties or identical properties, but diastereomers are not like that. They will be having different properties, that is they will be showing different melting points, different boiling points, whereas different solubility. They will also be showing different solubilities, and they will also have difference in their reaction towards most of the reagents. If they are reacting with a different reagents, they will, the action of these isomers, diastereomers, on different reagents will be different. When compared to the enantiomers, they will be showing different reactions with most of the reagents. This is a property of diastereomers, that is they will be having different properties, that is they will be showing different melting points, boiling points, and solubilities, and they will also differ in the interaction towards most of the reagents. And the last one we have is the mesocompounds. A compound with two or more chiral carbon atoms and also have a plane of symmetry is called as a mesocompounds. See here, first we need to know what is a plane of symmetry. Plane of symmetry means if there is a compound, if you fold the compound exactly at the center of the compound, you will be getting two equal halves, two similar equal halves, that we call as a plane of symmetry. See the example over here. Don't consider this mirror plane. See the compound without this mirror plane. You have two chiral carbon atoms. See this carbon atom, it is bonded to the four different groups: hydrogen, chlorine, methyl, and this whole group is considered as a fourth group. Means this carbon is bonded to four different groups. So this is a chiral carbon atom. And see the second carbon here. This is also bonded to hydrogen, chlorine, methyl, and this whole group is considered as a fourth group. Consider this molecule without the mirror plane. You will be getting two chiral carbon atoms. You have two chiral carbon atoms. Mesocompounds means they should contain at least two or more chiral carbon atoms, and plane of symmetry. See here now, if I am drawing the plane, mirror plane over here, if I fold the compound at this mirror plane, exactly we will be getting two similar halves. If I fold this here, you will be getting carbon atom on carbon, hydrogen on hydrogen, chlorine on chlorine, and methyl on methyl. So you will be having a plane of symmetry in the compound, as well as there will be two or more chiral carbon atoms in the molecule. Such type of compounds we call as a meso compound. So this was all about today's class. In the next class, we will see the next concept of the stereochemistry. Thank you.